I'm going to show you how you could use the Universal Law of Gravitation, which is this equation here, to determine the force of attraction between two objects given their distances. This equation works for weight, but in a question like this one, where you have two people, you wouldn't be able to use that equation because you have, if you look at the equation, you just have F equals mg, right? So you can't use that equation to solve a question like this. Or if you have two people and their centers are 2 meters apart and they each had a mass of about 100 kilograms, what is the force of attraction between them? So then in that case, you got to use this equation. So this is the universal law of gravitation. Okay? It's a function of big G, which is a constant, times the two masses over the distance squared. And it's a pretty simple equation to use. So if I look at this first question, I have two people that are situated 2 meters apart. So here's maybe one person, and here's another person. And it's got to be the distance from their centers. So that's the distance of 2 meters. Right? Always from the centers. Now, if I want to know, maybe this is someone you really like, and you want to know that, you want to impress them with your physics ability and say, this is the force of attraction between you and that person. It's very easy to work out. So you put in, so you have big G, which actually we already know what the equation is. So it's 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. So that's big G times the two masses, right? Because the equation you can see up here is big G, M1, M2. Now in this case, the two masses are exactly the same. So it's 100 kilograms times 100 kilograms. And this is all over R squared, or in this case, 2 meters squared. Okay? So we have 6.67 times 10 to the negative 11. Look, this is kilograms squared. So your kilograms will cancel out. And this is meters squared. So the meters squared will cancel out. So you're left with this. Over 4. Because 100 squared is 10,000, right? So it's going to be 6.67 times 10 to the negative 11 times 10,000 over 4. So if I simplify, 10, does anyone know what 10,000 is as an exponent? It's 1 times 10 to the, or 10 to the what? This is 10 to the 4. So this is 10 to the 4. So the numerator becomes 6.67 times 10 to the negative 7 newtons over 4. And now we can just simply divide 6.67 by 4, and that should be pretty close to 1.7, is it? Times 10 to the negative 7 newtons. Now, that's a very tiny number, which explains why you don't really feel that force of attraction between you and another person, because your masses are so tiny. You do feel the force of attraction between you and the Earth, because the Earth is way more massive than a 100 kilogram person, which is what you're going to see in the next calculation. So there's an example of just using the universal law of gravitation. Sometimes what happens with kids when they do forget often that the units have to be in meters, and sometimes they forget to square that. So remember, the distance has to be meters, it has to be squared, and it has to be the distance from their centers. Okay? So don't ever get tricked. It's got to be the distance from their centers.
So you
Yep.
use that one because it is long distance?
Can't use the weight equation here because you have two objects, and you want to know the force of attraction between two objects. Okay? It's not with you and the Earth. So it's different. It's between two different objects. I'll show you the connection between the two equations, though, because there is a connection between this equation over here, the equation for weight, and this equation. Because what do you notice is the symbol for each equation? It's the same symbol. It's F little g. That tells you there's a connection between the two equations. Otherwise, why else would they have the exact same symbol? So let's see what that connection is. Because we're going to use that connection to figure out the mass of our planet. Okay? So what we're going to do is actually derive a new equation with those two equations. Because we have an equation for weight, which is mg, right? And we have an equation for universal law of gravitation. I'm recording something. Yeah. Which is big G, m1, m2 over r squared. So we're going to derive a new equation. But before we derive a new equation, I'm going to ask you a simple question. See how this says m1, m2? So if I was, like, could we use this equation to figure out the force of attraction between you and the Earth? You can. But what would you need? Well, you would need your mass, you would need the mass of the Earth, and then you would need the distance from you to the center of the Earth, right? So if you were on a planet, you were on planet Earth, you would need to know what that distance is, right? You need to know the mass of the planet, mass of you, and the distance. So if we label you as M1, maybe that's you, then M2 would be the planet. So if I look at this equation, what would that M be? Well, that would be the same as M1, right? On the other side. That would be really you. Now remember, weight is the force of attraction between you and the planet Earth, or you and any planet that you're on. So the weight on the moon would be different because the value of g would be different, right? Little g would be different on the moon. Well, what we're going to do is we're going to set these two equations equal to each other. So my weight equation is basically u times little g, right? And that would equal big G times u times the mass, I'm going to call it MP, mass of the planet, because M2 is the mass of the planet. So I'm going to call it MP, all right? And this is over, well, what happened here? This is over r squared. Now, what do you notice? You have your mass on one side and your mass on the other side. So, you're irrelevant. Okay? When it comes to this equation, we are irrelevant. Okay? So now what you're left with is little g equals big G m planet r squared. I could rearrange, no, you can leave that as an equation. So in other words, you have an equation here that says something actually really important. One is, I can determine the gravitational constant, not the gravitational constant. I can determine little g on any planet in this solar system, as long as I know two things. And I'm talking about at the surface of the planet, okay? If I'm on the surface of any planet in the solar system, or anywhere in the universe, assuming the laws of physics are the same, I could determine little g there. Remember, little g is just the rate of acceleration. And for us, it's on the surface of the Earth. What is it again? 9.8. All I need to know is two things. The mass of that planet, or moon, or asteroid, and the radius of that object. That's all I need to know. Or, I can rearrange it and say, what if I want the mass of that planet, or asteroid, or moon? Well, then I could rearrange it to get this equation. All I have to do is visit some foreign planet or moon or whatever, drop an object. Now, why would I drop an object on the surface? Because what could you determine with something that falls? You can determine the acceleration, right? What do you need to know? Two things. How far it falls and how fast it falls. Remember this equation? Remember the drop equation? Remember that equation? If I go to the moon, let's say I want to know the mass of the moon. All I gotta do is fly to the moon, which I know is easier said than done. Take an object and drop it. As long as I know how far it drops and how long it takes to fall, I can figure out A. And A is the same as little g, right? This is the acceleration due to gravity. The radius, I can measure it, right? Now, I can maybe take a picture of the moon, maybe scale it, and figure out how wide the moon is and figure out the radius. So I can figure out the mass of any object as long as I know how fast things are falling at the surface and what the radius of that object is. So let's look at Earth. Let's determine the mass of Earth, okay? So what's the acceleration due to gravity at the surface? Okay. So the mass of the Earth will be a function of its acceleration due to gravity times the radius. Now, does anyone know what the radius of the Earth is? No? Okay, so the radius of the Earth is 6.3 times 10 to the 3 kilometers. Okay? Now, I wrote that on purpose. Because, what is this supposed to be in? Yes. Okay. Let's put all the units in too, by the way. And I ran out of room. Give myself a little bit more room here. Whoop, what happened? Whoa. Whoa, get back. Oh my lord, what just happened here? Okay. Now I'm just going to do undo. Undo, undo, undo. Don't you wish you had an undo button in your life? There we go, that's good. Okay. Or delete, so we said. Again. Whoa. Okay. So we left with this equation, alright? Now, it's going to be the mass of the planet. So what do you think will be left in terms of your units? It should just be kilograms, right? So you're going to have to, well, first off, before we continue, we need to convert this because it's got to be in meters. So if it's 10 to the 3 kilometers, how many meters are in a kilometer? 1,000. So it will be 10 to the 6 meters. One day I will learn how to draw a straight line. Now, so I'm putting all the units in, but really, this is going to be meters squared. So that's going to cancel out. I have newtons, but remember what a newton is? A newton is what? Kilogram meter per second squared. So what you'll have left is you're going to be, when you do all of the elimination of all of the units, you're going to have basically kilograms left when everything else gets eliminated. So you'll be left with just kilograms. Alright, so let's finish this. So little g is 9.8. What is the square of 6.3 times 10 to the 6? So 6.3 times 10. So there's two ways you can do this. One, you can take the square of 6.3 and then times 10 to the 12. Or you can just plug it in your calculator. So what do you get?
4 times 10 to the 13.
So 3.9 times 10 to the 13. And that's going to be over 6.67 times 10 to the negative 11. And then this is going to be kilograms. Okay. Are you guys okay with working with exponents? I'm going to assume you are. If you're not, come and see me. We'll talk about how to manage that. Okay. So let's just look at the numbers. For me, this is simpler. So what's 9.8 times 3.9 divided by 6.67? Let's just look at the numbers. 9.8 times 3.9 divided by 6.67. What is that? Forget the exponents. 5.7? Okay. Now let's look at the exponents. What's 10 to the 13 divided by 10 to the negative 11? When you divide exponents, what do? Okay. So what's 10 to the, so 13 minus negative 11 is? So that's our answer. Okay. That's the mass of our planet Earth. Now we're off by a little bit. Yeah, I think the mass of planet Earth, I think it's 5.8. Someone can double check that. But this is what you would do to determine the mass of any object. Okay? Or if you want to figure out the acceleration due to gravity, you could still use this equation, but you would use, where do we put it? You would just isolate for r squared. Okay? So I'm going to stop there. Keep it nice and short. And that is it.